Good morning. It's of course a great honor to be here. Besides on the poster introducing this workshop, you saw a tiny sample of Noga's theorems. One thing which wasn't explicitly celebrated there, but only hinted at, was his wonderful students. So of course, several of them have organized. But today I want to describe some joint work with one of his other students, Eyal Lubetzky, along with the others. So I'll describe two works, one with Eyal on Ramanujan graphs, and one with Eyal and also Nathaniel Berestycki and Alan Sly on random graphs. In both cases, we will focus on the behavior of random walks on these graphs. So, let me start. Okay. So we will be looking at mixing time of random walks, and specifically the cutoff phenomena, which I will define as a gauge for delicate properties of the geometry. Will survey this phenomenon on Erdős-Renyi random graphs, on random deregular graphs, and specifically on Ramanujan graphs, which are not necessarily random. We'll measure convergence of equilibrium using the most standard measure, the total variation distance, which is also the same as half the L1 distance. So this is the distance between two measures, is the maximum difference of mu a minus nu a, and it's also just half the L1 distance between the two measures. And then T mix of epsilon is the first time when the distance between the distribution at time t and the stationary measure mu are less than epsilon. Now, since we will be talking about simple random walks on graphs, the stationary measure is just proportional to the degrees, and of course, in the regular case, it's a uniform measure. So that's this measure, this target measure mu, and we are asking how close is the distribution at time t to mu. Now here, the definition of mixing time, the classical definition, involves looking at this from the worst starting point. So we maximize over x0, but later we'll want to also look at this for typical x0, not just the worst ones. Okay? And one phenomenon that we'll focus on is the cutoff phenomenon, which was first introduced in works of Diaconis, Shashahani, and Aldous in the early 80s. So what is the cutoff phenomenon? It means that the mixing time is asymptotically not dependent that much on epsilon. So the setup is we don't think of one graph, we have a family of graphs, a sequence of growing graphs, and we're measuring T mix of epsilon for each graph. And so this T mix of epsilon implicitly also depends on n, the nth graph. And we compare it to T mix of epsilon prime, which also depends on n. And the ratio of these two should go to 1 as n goes to infinity. So that is what cutoff represents. And this can be measured in terms of the decay of this function, the distance. So what you see here is the graph of the distance at time t to the stationary measure. So this maximum that you see here, what is the distance? So the distance always, once it reaches strictly below a half, it has to decay exponentially. But in the cutoff case, it decays faster. You have this kind of rapid decay. So if you look at how long till you got to epsilon or to epsilon prime, these are two times whose ratio is getting close to 1 as we go along the sequence of graphs. So the first example of cutoff was random transpositions on the symmetric group. So you have n cards, choose one with your left hand, one with your right hand, and transpose. It might be the same card, so then you don't move. And clearly you need at least n log n over 2 steps because of coupon collector in order to mix this chain. But using representation theory, Shashani showed that, in fact, n log n over 2 is enough. So the mixing time is asymptotic to n log n over 2, not caring about what epsilon you are looking at. So the epsilon only affects the lower order terms. In a way, a simpler example is a lazy random walk on the hypercube. So you have the hypercube, n-dimensional hypercube. Each time with probability half you stay in place. With probability half you move along one of the edges. So lazy simple random walk on the hypercube mixes again in n log n over 2 steps. And there are other examples. Interestingly, all the classical examples were random walks on graphs whose degree goes to infinity. And let me just give a quick preview. There's a reason for that, because the proofs were based on matching L1 and L2 bounds, and this matching gets more problematic when the degree is bounded. So lower bounds were obtained by showing specific sets where the two distributions differ. Upper bounds were obtained usually spectrally, and we know that computing with spectrum, it's much easier in L2 than in L1. So if the L2 and L1 mixing times match, then you have a recipe to prove cutoff. If they don't, there's some difficulty with this approach. And indeed, until 2009, there was only one isolated example of a bounded degree graph where there was cutoff. All the classical examples were high degree. So again, in this slide, I'm emphasizing this is the example of the hypercube, the classical example where we have cutoff. This is a classical example where we don't. Random walk on a cycle mixes in time n squared. But if you want to get within epsilon, the n squared gets multiplied by a log 1 over epsilon. So there is dependence on epsilon. And kind of with these examples, the philosophy is that cutoff is connected to high-dimensional behavior of the chain, that mixing isn't coming from that mixing is coming from a cooperation of many things that have to go together, and lack of cutoff is indicative of low dimension. But this is very rough. One idea is, well, maybe high dimension represents approximate high multiplicity of lambda 2. So coming back to Latti's talk, but it won't be exactly the Colin-Deverdier number, but it suggests some connection along these lines. Okay, and this will appear in the later examples. So one setup that looks simple is a regular expander, right? So we have an expander graph, as mentioned in Latti's talk. So we're going to think of a sequence of deregular graphs such that the spectral gap is bounded below, or in other words, the relaxation time, which is the inverse spectral gap, is bounded above. In such graphs, we know that on the one hand, the diameter is log n, so the mixing time is at least constant log n. And on the other hand, the spectral assumption easily implies an upper bound of order log n on the mixing. So you have upper and lower bounds, which are constant multiples of log n, and these constants don't depend on epsilon. So although this doesn't tell us cutoff, it tells us that things can't be as bad as on the cycle. The ratio T mix epsilon and T mix epsilon prime is bounded. This is called pre-cutoff, but doesn't tell us if there is cutoff. So on this question, one natural case to look at is a random deregular graph. So these have been known to be expanders since, well, Pinsker gave the first construction of a random deregular graph that's an expander. A really uniform deregular graph was analyzed by Bolobash, and in his work and following up work of Broder Shamir, it was shown that indeed the random deregular graphs are expanders with high probability. This, I'm going to skip to the conjecture of, so this direct conjectured in 07 that the mixing time of simple random walk on the random graph, so say you take a random cubic graph, it should be 3 log base 2 of n, with a corresponding conjecture for higher d. So you see there's no appearance of epsilon here, so this conjecture is basically including cutoff at this time. Now this is really the earliest possible time you could have mixing on a cubic graph, because this cubic graph will have, the diameter will be log base 2n, so you have to move log base 2n away from the starting point, but a simple random walk can move at speed at most 1/3, because even if you are in a tree, you move with probability 2/3 further from the starting point, 1/3 back, so the speed is at most 1/3. So this kind of 3 log base 2 of n is absolutely the fastest it could mix. And as direct conjectured, there is a cutoff for almost all graphs, so a proportion going to 1 of graphs. This was proved by Lubetzky and Sly in 2010. And in general, if d is bigger than 3, then this factor 3 is replaced by d over d minus 2. This just comes from the speed of random walk on the tree. If you have a deregular tree, the random walk moves away from the root with probability d minus 1 over d, towards the root with probability 1 over d, so the speed is d minus 2 over d. And the inverse of that gives you some, I'm jumping ahead here, sorry. This is, let me get the right buttons. Okay, so the speed of that gives you the suggestion of what is the constant here, d over d minus 2. Now, along the way of proving this result, they first analyzed the non-backtracking walk on these graphs. So the non-backtracking walk each time takes a uniform step along an edge, but not the edge that the walk just came on. Okay, so we'll see this more formally later, but I think this is clear. So you have a particle moving. Each time it chooses uniformly one of the neighbors, excluding the one it just came from. Okay, so that's the non-backtracking walk. And if you look at the non-backtracking walk, it also has cutoff. It's also a Markov chain. And it has cutoff at an earlier time, so log base 2 of n in the 3 regular graph, or log base d minus 1 n. So that was in that paper. And so that's the case of random deregular graphs. One can compare the behavior of the non-backtracking walk and the simple random walk. And indeed, as was true in this example, and as we'll see in further examples, for proving mixing time, if you can understand the non-backtracking walk on a deregular graph, you can then understand the simple random walk. Because you can lift the walk to the covering tree, and if you are on a covering tree, so just on a deregular tree, a non-backtracking walk just moves forward. A simple random walk is still easy to understand, and a simple random walk at time t, it will be distributed on some random level, but the level will be about d minus 2 over d times the level, time multiplied by the time. And given the level, it will be uniform on the level. So you can easily infer from that that the distribution of simple random walk at any time is a mixture of the distributions of non-backtracking walks at earlier times, and the earlier is by this factor d minus 2 over d. So I realize this is very, very sketchy, but the point is, if you understand mixing of non-backtracking walk on a d-regular graph, you can infer for total variation, you can infer mixing of the simple random walk by just multiplying by a d over d minus 2 factor. Okay, so let me switch to emphasizing d-regular graphs which are not random. Okay, so this is work with Eyal that we were working under a deadline because we wanted to get it ready for this birthday. And so let's quickly recall some basic facts about expanders that we will need. So we said already what's a d-regular expander, and the Alon-Milman and Alon theorems were mentioned that this is equivalent to the lack of sparse cuts. Directly relevant to what we will discuss here is the Alon-Boppana theorem that says that for any d-regular graph, lambda 2 is so here I'm talking with the lambda 2 I'm talking about here is not for the normalized matrix, but for the adjacency matrix. So lambda 2 is at least 2 root d minus 1 minus a small correction which tends to 0 as n grows. And there's also a relevant refinement of this due to Serre, which says that, in fact, if you take any small interval near 2 root d minus 1, say 2 root d minus 1 minus epsilon, beyond that you have a positive fraction of the eigenvalues. So that's kind of how low lambda 2 can get. Conversely, a Ramanujan graph is a graph which gets that low. So that's a connected d-regular graph such that every eigenvalue except plus minus d, so it's allowed to be bipartite if you have a minus d. So you always have the plus d, of course. All the other eigenvalues should be in this interval smaller than 2 root d minus 1. So these graphs were first named by Lubetzky-Philip-Sarnak, who gave the first construction along with Margulis in a separate paper. And these were for if d minus 1 is prime. Then there were other works for other values of d, and in particular, just a couple of years ago, Marcus Pillman's Srivastava showed that there exist Ramanujan graphs. Well, these were bipartite for all d from 3 on. Okay, so that's the basic history. Here is an attempt by Eyal to picture some of these the local geometry of some of these graphs. So this is the Lubetzky-Philip-Sarnak graph. It's 6 regular, about 12,000 vertices. So they're not all here. But if you look at one node, then locally you have a tree structure near it. So that's easy to understand. But really, we want to understand what's going on here. And this is also a different attempt to visualize a small part of the graph. Now, here is another picture of the spectral measure. And this pictures both the LPS graph you saw before, so it's in the foreground. And the point is to see the high multiplicities of the eigenvalues here. And in the background, you see a random lift of a 3 regular Peterson graph. Such random lifts are not guaranteed. So we have Nati here, who's responsible for a lot about random lifts, but there's no theorem yet that assures us such a random lift will be a Ramanujan graph. However, if you do the 1,000 lift of the 3 regular Peterson graph and you have a co-author who knows how to analyze these things, then it turns out that this graph has this particular example is Ramanujan, and in the background you see the spectral measure of that, so it's quite different, yet that's also a Ramanujan graph. So So this is a classical theory by now going back to the 80s, but there's various motivations for renewed interest in these graphs. The probabilistic one I will describe next, but also there are applications to cryptography, to quantum computing, and you'll hear more about those in Peter Sarnak's talk. There are also new insights about distances in arithmetic Ramanujan graphs, these original constructions, again due to Peter and his students and collaborators. In particular, there's recent work of his student Sardari that exhibits some p+1 regular Ramanujan graphs that have diameter at least 4/3 log base p of n. So p here is d minus 1. And I guess the conjecture, as I've heard from Peter and from Sardari, the conjecture now is that the classical LPS graphs indeed have that kind of asymptotic dimension. There's some numerical evidence as well, asymptotic diameter, sorry. There's some numerical evidence as well. We won't really touch on the diameter, but come back to the issue of typical distances that are more relevant to this work. So I'm recalling again the definition of cutoff is that T mix epsilon doesn't depend on epsilon, so T mix epsilon and T mix epsilon prime have ratio going to 1 along a sequence of graphs, and our goal will be to understand cutoff in different graphs, in particular the Ramanujan graphs. And one conjecture which is still open that I made in 2004 is that cutoff holds for all transitive expanders. And this we still don't know, and until this work, we didn't know even a single example of a transitive expander family with cutoff. Now, since we mentioned Ramanujan, it's still not known whether random deregular graphs are Ramanujan with some fixed positive probability, but a famous conjecture of Noga proved by Friedman is that they are weakly Ramanujan, so with high probability, lambda 2 is 2 root d minus 1 plus an error that goes to 0. So that's about the random ones. Now we're going to look at random walk on these graphs and the distance from equilibrium for the random walk. And as I hinted before, the standard method of comparing L1 and L2 doesn't work here to prove cutoff. So here is the graph in the LPS, just computed numerically. And you see that the distances in L2 go down considerably later after the distances in L1. So there's no tight match here. And this is the asymptotic behavior. So even as n tends to infinity, you have cutoff both in L1 and in L2, but it happens at a different time. And there's the ratio doesn't go to 1 of these asymptotic mixing times or cutoff times. So the classical approach of using L1 from below, L2 from above, and matching them doesn't work. However, as we'll see, it does work going to non-backtracking walk. So if you look at the non-backtracking walk, then our finding is that this approach does work. You can do the spectral analysis, compute the L1 and L2, they do match, and that allows you to get the cutoff in L1. So that's the plan, and I'll say some more about that. So here is the main result. On any sequence of deregular non-bipartite Ramanujan graphs, simple random walk exhibits cutoff. So, and T mix of epsilon is, as we suggested before, d over d minus 2 times log base d minus 1 of n, the same as in the random deregular graphs. And again, for any epsilon between 0 and 1. Now, the non-bipartite, of course, if the graph is bipartite, simple random walk won't mix at all. But it's not a fundamental issue if you change the walk by just making one step lazy. Just the first step, with probability half you stay in place, with probability half you move. Then you continue regularly. That's enough to retrieve the same result in the bipartite case. So there's no real difficulty with the bipartite graphs. And the main theorem extends also to the weakly Ramanujan graph, so we get another proof of the Lubetzky-Sly theorem, though kind of roundabout and harder. But in particular, there are other examples of weakly Ramanujan graphs. In particular, all the random lifts, if you fix any Ramanujan graph, a finite Ramanujan graph, then take its random lift, that is going to be itself a weakly Ramanujan graph by results of Friedman and co-authors, and then our result applies here to show that all such random lifts will have cutoff. One can also allow some violations of the Ramanujan condition, so we can have some number, any subpolynomial number of eigenvalues that are away from the Ramanujan interval, as long as the graph is still an expander, so they can't stick to D, but as long as they're bounded away from D, they can be arbitrarily large, and their number should be n to the little o of 1, then the theorem still goes through. One corollary, since this is combinatorics is the center here, one combinatorial corollary I want to mention is about typical distances. So if you take a Ramanujan or a weakly Ramanujan graph and fix any base vertex x and look at so the diameter measures distance to the furthest y, but suppose I'm willing to give up a negligible fraction of vertices, then the distance becomes log d minus 1 of n. So the number of y's so that the distance is not log d minus 1n up to a 1 plus epsilon, this number is negligible, little o of n. So we really have this kind of behavior that is well known for the random deregular graph holding for all weakly Ramanujan graphs. And this is the consequence of not the theorem I stated before, but its proof, which is based on non-backtracking walks, since non-backtracking walks directly lead to estimates on distances. I should mention that a different proof of this was obtained independently by Sardari with a different method using Chebyshev polynomials, so not via the non-backtracking walk. You can find both papers on the archive. Now, the non-backtracking approach that we use gives you some additional information. So not only for any two vertices, but for any two directed edges, you can go from you can find a path that takes from one directed edge to the other directed edge and has this length log base d minus 1 of n. And so just to give you an example of how that can be used, suppose your graph has high girth, like the bipartite Lubetzky-Phillips-Sarnak graph. So if the girth is bigger than log d minus 1n, then you get that for you fix one edge, and you take the other edge to be generic, so with a tiny number of exceptions, you take E1 and E2. So E1 is arbitrary, E2 then has to be chosen outside the negligible set. And then there is a simple directed cycle that goes from E1 through E2 and back of length 2 log d minus 1n. So you just easily get from this corollary. Now, let me say that when going from two directed edges, you cannot do it if you just know that you can go from vertices, because it's very hard in these high girth graphs to turn around. So if I know I can go from one place to another, I don't necessarily know that I can go it with the direction that I please. So this, and if you try to trick the problem and say, well, I want to aim to the base vertex of the edge, well, what if you come from the wrong direction and then you cannot reverse? So, but the non-backtracking walk analysis allows us to get these corollaries. We can also understand the distances in all LPs, and really, there is cutoff in every LP for p bigger than 1. That is not a surprise. But the cutoff times really depend on p and vary with the different p's. So if you measure, instead of L1 distance to the stationary distribution, you measure it in LP, you get cutoff. But this is a picture in the LPS graph. But the same thing holds asymptotically, that the decay happens at different times for different p's. And one can write a formula, which I won't trouble you with now, of when is the mixing time depending on the LP that you measure. But really, if you take, say, the L2 mixing time, it has to be strictly larger for any deregular graph. So if I take a 3 regular graph, the L2 mixing time just has to be bigger than 3 log base 2 of n, because the possibility of backtracking is very serious in a bounded degree graph, and it really slows down the decay of the L2 distance. So as I've emphasized, the key tool is looking at the non-backtracking walk, and then one deduces L1 mixing for the simple random walk from the non-backtracking walk. When did we start? Okay. So the non-backtracking matrix, so the adjacency matrix for the non-backtracking walk is simple to write down. So if I have two directed edges, u, v, and x, y, this will be 1 if v equals x. So this v has to equal x. But u should be different from y, right? This is the transition matrix for the non-backtracking walk. And there is a famous connection between eigenvalues of b and eigenvalues of a. So for any eigenvalue lambda of a, there are two corresponding eigenvalues of b, which satisfy this quadratic equation. And b is much larger, so it has additional eigenvalues, but they are the trivial ones of d and possibly minus d, and then plus minus 1s. So the other eigenvalues are really not important, as it turns out. But these are the important ones. So for every lambda, we get 2 of these. And really, in our proof, a key role is played by the precise spectral analysis of the non-backtracking walk, or Jordan form, that works in any deregular graph. So this following lemma holds in every deregular graph. It's particularly effective in the Ramanujan case. So what is the statement here? So note that the non-backtracking walk, it's not reversible. So the matrix B is not symmetric at all. However, it's not that far. It's not diagonalizable, but it is orthogonally equivalent to a matrix which this very nice Jordan form. So you have this d minus 1, the largest eigenvalue. It has to be there. So this is the, I guess okay, so we have d minus 1 here. Then there are these plus minus 1s, which will turn out to be unimportant. And then the rest are 2 by 2 Jordan blocks. So on each Jordan block has these 2 eigenvalues corresponding to 1 eigenvalue of A. So this is our solutions of the quadratic equation I showed you before. And there is one additional element off-diagonal. And all these off-diagonal elements, in the Ramanujan case, they're all the same. They're all exactly d minus 2. We can write what they are in general, but in the Ramanujan case, they're just all the same. And since they are rather benign, this allows us to work with the matrix almost as if it's diagonalizable and just do the usual spectral calculation of the random walk distribution. So this is some picture of these eigenvalues. So I should emphasize that all the interesting eigenvalues, all these theta, in the Ramanujan case, they all lie on the circle of radius root d minus 1. And they come in these conjugate pairs. So now suppose we want to analyze. So mu t is the distribution of the non-backtracking walk starting from an edge xy at time t. And we want to analyze the L2 distance to stationarity of this measure. So if we were in the diagonal case, we know how to do these calculations. You just pass to the, using all the diagonal elements, you get a certain sum. This is the contribution of the unimportant eigenvalues, the plus minus 1, and turns out to be negligible, because the t we're going to take will be very close to log d minus 1n, so this factor will turn out to be negligible. The main factor comes from these important eigenvalues I mentioned, the theta I, and you just easily compute it. In the diagonal case, this time is indeed sufficient to make it small. Now, since we are not in the diagonal case, there is a correction, which I didn't write down now, but because we understand exactly what is the correction, a number is very easy to take to a high power, but a 2 by 2 matrix is also, a triangular 2 by 2 matrix is also very easy to take to a high power. So when you do that, the same kind of calculation goes through, except here the correction is not just a constant, but we need a log n. But we can live with that. So I'm omitting the more precise calculation. You can find it on the archive, but it just is a small variation from the diagonal case. And I want to mention one useful tool here, which is from this book, which after 19 years it's just been completed and sent to the publisher, Probability and Trees and Networks with Russ Lyons. And so among the 720 pages there is the following fact, that if you take B, the non-backtracking matrix, and it's well known to be invertible, if you take this B and add D minus 1 B inverse, this matrix is symmetric. So of course, we know that the original matrix A is symmetric, but that's A is on a different space, on vertices. So it's useful to have a symmetric matrix to work with, which is on the same space of directed edges, and this C is symmetric. In fact, this is an explicit, when you calculate it, you can easily see that it indeed comes out symmetric. And so we know that it has orthogonal eigenvectors, and it's diagonalizable. And the eigenvectors of C are just the same as the eigenvectors of B, and the transformation of eigenvalues is simple as well from this formula in the functional calculus. Okay, so in the last k minutes, let me go back to say something about random graphs. Hopefully. Okay, so in the Erdős-Renyi graph, we have the three phases, and we're going to focus on the supercritical phase where we have a giant component of order n, and okay, so we're going to focus on the giant component of order n here. So P is lambda over n. Lambda is bigger than 1. And in this case, the mixing time, so the critical case has a whole different story that I can't get into, but the supercritical case was, so we have a component of size, linear size, and the mixing time is order log squared n. And this was proved independently by Funtulakis-Reed and independently slightly later by Benyamini, Kozma, Wormald. And it's easy to see the lower bound of log squared n, because if you take the random graph and you start at you have these long paths of length log n that stick out of the giant component. And if you start at the end of such a path, well, it will take log squared n to reach the main body. So that gives you a lower bound of log squared n. So the non-trivial content of these theorems is that once you reach the main body, there's no delay bigger than log squared n. There's still log squared n happening even if you start in the 2-core. If you start here in the middle of the 2-core, you still take log squared n to reach the main body. So even if you remove all the leaves and stay with the 2-core, the mixing time would still be log squared n. Still, Funtulakis-Reed asked, is this large log squared n due to starting at bad points? And indeed, that's true. That's what we prove with Eyal, Berestycki, and Sly. The proof is based on a structure theorem that, or the proof uses, I shouldn't say based, but it uses a structure theorem where we can take this giant component and separate it into so the giant component can be built by taking an expander which is a random graph with a known degree sequence, stretching the edges to get the two-core, and the stretch can be done independently up to contiguity, and then adding independently Galton-Watson trees at the nodes. I won't have time to delay this, but the point of showing this picture is that a key step in understanding random walks on the giant component is the simpler task of understanding random walk on a random graph where the degrees are all 3 and higher. So a random graph with a known degree sequence, which Bolobash's configuration model tells us how to pick such a graph. Okay, so in these graphs, unlike the regular case, mixing is not determined by how far you are from the origin. So the random walk reaches the maximal distance from the origin well before it is mixed, well by a constant factor. So there is something much more subtle going on in the irregular case, and to say it very quickly, even when you reach the maximal distance from the starting point, you're not at a typical node, and the reason is there are very few paths connecting you to the starting point, and these paths have atypical degree statistics. And until the degree statistics settle, it takes longer. Now, the way we can reach this is via a connection to Galton-Watson trees. So I'll finish by just stating and explaining what are the terms in our main result, which says that there is cutoff when you start at a typical vertex. So in this case, the mixing time from the worst vertex, there is no cutoff. The mixing time is log squared n, but no cutoff. But if you start from a typical vertex, then there is cutoff. The mixing is much faster. It's a constant times log n. And what is this constant? It involves two interesting quantities. One is the speed of the random walk, and the other is the dimension of harmonic measure. So the speed is easy to understand. We saw already in the regular case the speed played a role in the mixing. But the dimension of harmonic measure is more subtle. You see, when a random walk walks on a deregular tree, it spreads uniformly over the tree. But when the tree is, say, a Galton-Watson tree, which is not regular, the random walk tends to not spread uniformly. So this is in work in the 90s that I did with Russ Lyons and Robin Pimentel. We analyzed random walk on such a Galton-Watson tree and showed that the kind of irregularity of the tree means that the random walk stays on a really smaller subtree of smaller exponential growth. So the Galton-Watson tree has some exponential growth, but this tree has the random walk has this non-uniformity, which you can kind of see here. And this non-uniformity implies, when it gets iterated, that there is a really smaller subtree, of smaller exponential growth, where the random walk is confined to. And the growth of that tree becomes the relevant quantity rather than the growth of the whole Galton-Watson tree, which approximates the local behavior of the random graph. So, so there are some rather involved details about calculating this dimension, and I won't be able to get into that. But as I mentioned, this is based on a paper called Ergodic Theory on Galton-Watson Trees, which was with Lyons and Pimentel in '94. And really, in the present work, we had to go back, revisit that work, and tighten some of the estimates, because those were all asymptotic as we had the one random tree had to go to infinity. Here, we had to get estimates that could be transferred to the finite graph. But luckily, things could be tightened. And now going from this case to GNP presents some further difficulties because of the stretching and the hanging trees that one has to handle. And the key is that although in the random graph we have the long paths of length log n, which cause a lot of trouble, the random walk started from a typical vertex doesn't see these. The longest long path it sees is log n, because we only run it for time log n, so it just doesn't see these really bad areas, and so we can couple it to a random walk on the graph with much less stretching. This is a very short sketch of the key thing, and the same is true for these hanging trees. There are some really bad hanging trees of size log n, but the random walk started at the typical vertex never comes near any of these trees. The worst ones it will see is log n, and that can still be managed. So let me jump to the end now and just mention two open problems, one of which we've just made some progress on. So you want to compare, if I am on a regular tree, it's obvious that the non-backtracking walk is mixing, or if I'm on a regular graph, then the non-backtracking walk mixes faster than the simple random walk. But if in the irregular case, there is a complication because although the non-backtracking walk moves faster, it is also less smart about where it moves. The simple random walk, when it goes to an area which is sparse, it tends to go back. While if it goes to an area which is rich, it moves forward more. And that has to be balanced with the fact that it moves more slowly. So this backtracking is kind of, the simple random walk is more selective on where it goes, but the selectivity slows it down. So you have to compare these two effects. And it seems intuitively that the slowing down is more important. So the selectivity doesn't pay off. And that's what we conjecture. So formally that the non-backtracking random walk will mix faster. This can be expressed as a fact about Galton-Watson trees. You have a Galton-Watson tree, you run a random walk, and you look at how does the entropy of this random walk grow, and the entropy of the non-backtracking walk should grow faster. This is what we believe. So far with Eyal and Anna Ben Hamu, we've been able to prove it for the case when all the degrees are at least 3, but degrees 2 still present an obstacle. Let me stop here, and happy birthday, Noga.